All right, this was our result for a L length rectangular discrete time pulse, and this is the discrete time Fourier transform. And I mentioned that we would really like to get this into a form that's a little more useful. And what we're going to do is try to separate out the amplitude part from the phase part. And here's how we do this. And again, this is another skill, and I'll have a homework problem very similar to this that is pretty important to have. It's one of those you didn't realize you needed. Um, let's look at the numerator to begin with. This thing up here, and let's see if we can write it in a little bit different way. We've got 1 minus e to the minus j omega L. I'll just point out that this is e to the j0 minus e to the minus j omega L. And what we can do, what I'm going to try to do is get this into the form of an Euler identity. And it kind of looks like a sine. You remember a sine is sine of x is, well, if I said 2j sine of x is e to the jx minus e to the minus jx. So it kind of looks like that, but the exponents don't work out quite right. And my contention is that if we're clever, we can factor out something and get this into a form that looks like that. So consider that I can write this as following. E to the minus j omega L over 2 times e to the j omega L over 2 minus e to the minus j omega L over 2. You see what I did? I just factored out an exponent. If you multiply this through, this times that, you get 1. This times that, you get e to the minus j omega L. So I haven't changed anything, but what I've done is I factored it so that in here we get the Euler identity, 2j sine omega L over 2. Okay, so that's kind of what we want to do. In fact, it's exactly what I want to do. Let's do it with the denominator term. So this is the numerator. We do the same thing with the denominator. We've got 1 minus e to the minus j omega. Note that this, what I want to do is I want to come up with a factor that's kind of halfway between, look at the numerator term, I came up with a factor that's halfway between the lowest exponent and the highest exponent. So halfway between 0 and omega L is omega L over 2. Well, now I've got a very similar thing. This is e to the j0. What's halfway between 0 and omega? Well, it's omega over 2. So I can write this as e to the minus j omega over 2 times e to the j omega over 2 minus e to the minus j omega over 2. Okay, and that's equal to, again, that's an Euler identity. Oops, let me get my eraser out and fix that up a little bit. Got the parenthesis in the wrong place. All right, so that's just the Euler identity, and we can write this as e to the minus j omega over 2 times 2j times sine omega over 2. And I really don't need the I don't really need this parentheses anymore because we've collapsed this whole thing into a single sinusoid. So that's the benefit of doing that. Now we've got a numerator result and a denominator result, and we can put them together into this equation and see what we get. It ought to simplify a whole bunch. Okay, so we've got x e to the j omega, and the numerator is this thing, 2j e to the minus j omega L over 2 times sine omega L over 2. And the denominator is this thing. We've got 2j e to the minus j omega over 2 sine omega over 2. All right, and of course, what's going to happen is the 2j's cancel, and we can bring this exponent, we can merge these two complex exponentials and just subtract this exponent from that exponent, and we get e to the minus j omega times L minus 1 over 2, and then I have this ratio of sinusoids, sine omega L over 2 over sine omega over 2. All right, that looks pretty darn good. This is the thing we wanted. It's some quantity that's purely real. And we have some quantity here that has all of the continuous phase information. It's contained in that exponent. Okay, so that's pretty darn good. Let's talk. I'll come back to this in a second. I wanted to do another example of this business where we're converting things that look like that into an amplitude part and a purely real amplitude part and a phase part. So let me just work one more example because I've got a couple homework problems that are sitting there waiting for you. Things that are a little more complicated. And let me do just one little more complicated. Oops, switch back to my black pen. So let's start with x of n, and it's 5 minus 4, comma 0, comma 4, comma 5. And there's the n equals 0 place. Let's see if I can graph this thing. And so we've got a 5 minus 4, a 0, a 4, and a minus, oops, that's supposed to be a minus 5. So let's get down here, right there. So that's this thing, x of n. The Fourier transform is x e to the j omega, and again, it's just the sum over all time of x of n e to the minus j omega n, and that's 5 minus 4e to the minus j omega, n is equal to 1. We pick up a 0 there, and this is plus 4e to the minus j 3 omega, and this is minus 5e to the minus j 4 omega. All right, so there's the Fourier transform. Is it possible to factor a common term out of there so that we wind up with a couple of Euler identities? And what you're looking for are pairs of complex exponentials. There's a pair. Maybe that will turn into a, and these have negative signs, so that will turn into a sign, and maybe this 5 and that 5 will turn into a sign. What you're kind of looking for to make these things work is either odd or even symmetry about some location. Here there's odd symmetry about n equals 2. And this also works if there's even symmetry about a place. All right, so let's explore this a little more. Up here, when we looked at these previous examples, we found a common term that was halfway between these two exponents. Okay, and that turned out to be the thing that when we factored it out, left us with an Euler identity. Well, the same thing's true here. I want this term. I want this guy and this guy, when I factor something out, to be an Euler identity. And I think clearly the middle value of the exponents is that's minus 1 omega and that's minus 3 omega. So I need minus 2 omega. Okay. What about this? I'm going to want this guy and this guy to be an Euler identity. And what's the middle exponent? This is 5e to the j0, and this is 5e to the minus j4. Midway between 0 and 4 is minus 2. So we get the same factor we can pull out of this thing. Let's see if it works. So I contend that we can write this as e to the minus j 2 omega. That's the guy we found that was midway between this 4 and that 4, and that 5 and that 5. All right, so we get e to the plus j 2 omega. That's, and I need a 5 there. I've got minus 4e to the j omega. I've got plus 4e to the j omega. I'm factoring this as I go along, and then we'll talk about it. Minus 5e to the minus j 2 omega. Now, assuming we can read this, let me touch that. Let me get rid of that. That's supposed to be a plus sign, but it's just kind of confusing. All right, let's see if I did it right. And when you do it the first time, it'll take a little bit more thought, but I've done this a bunch of times. If we multiply this through, we see that, we hopefully will see that we get the same thing we started with. So this term times this term, minus j omega plus j omega, minus 2j omega plus 2j omega, will get e to the j0. Okay, that's what we started with. This times that should give us e to the minus j omega, and it does. This times this term should give us e to the minus j3 omega, and it would if I put a minus sign there. And this times that should give us e to the minus j4 omega, and it does, because we got minus 2 omega there and minus 2 omega there. All right, so we're almost done with this. We can clearly write this as this term is an Euler identity, and that's equal to a minus 4 times 2j sine omega, and those two guys combine to be a plus 5 times 2j sine 2 omega. All right, so let's write this whole thing out. We've got j e to the minus j2 omega, and then we've got times 10 sine 2 omega minus 8 sine omega. Okay, so that's what we wanted. Here we have a purely real function of omega. This is the amplitude part. And this part, we can even simplify this. Remember, j is equal to e to the j pi over 2. So this part, let's go over here and do it over here. We've got e to the j pi over 2. That's this j, and e to the minus j 2 omega, and that's equal to e to the j pi over 2 minus 2 omega. All right, so final result, x e to the j omega is e to the j pi over 2 minus 2 omega times this amplitude part, 10 sine 2 omega minus 8 sine omega. Okay, so that's a good skill for you to learn.